So I want to talk about representations of p-adic groups. So for me, throughout this talk, K should be a finite extension of QP, a p-adic field. K contains a ring of integer O, which contains a uniformizer pi. And I denote the residue field by FQ. And then the main object for this talk will be denoted G, which is a connected reductive group over the local field K. So what is the goal? The goal for a long time was and still is that we want to construct all smooth, irreducible, complex representations of the group G of K. So in this talk, I look at complex representations. So the coefficient should be complex in the morphism of complex vector spaces. And smooth means is always that the stabilizer of every vector in our representation space should be open, so that we have a reasonable category to work with. And so there's a certain approach to this. We know that there are certain building blocks. And the building blocks for these representations, they are called supercuspidal representations. More precisely, what do I mean by building blocks? I mean that if you take an arbitrary irreducible representation, so for me, supercuspidal now for this talk means irreducible. If you take an arbitrary other irreducible representation, then you can embed it into the parabolic induction from some parabolic subgroup to the whole group of some supercuspidal representation, sigma. Sigma is a supercuspidal representation of the levy. So this means if you want to construct all representation, you want to construct the supercuspidal representation, then you can embed other representation inside the parabolic induction. And that's a different question, how this induction decomposes. But so in order to construct representations, we are really concerned with constructing supercuspidal representations. And that's a very mysterious thing to do. So for a long time, we didn't know how to write down these supercuspidal representations because they are not induced. So the definition of supercuspidal, one possible definition is just to say you cannot embed it into an induction from a proper parabolic to a group. So there's no easy way to write them down. So the way people do it usually is via compact induction from a compact subgroup. And for GLN, the story now is well known for more than 25 years. Thanks to the work of a lot of mathematicians like Hauer and Moy and Bushnell and Kutzko, and many others were involved in this. And the story for classical groups is known for about 10 years now, thanks to Sean Stevens, who adapted the approach for GLN and made it work in a setting where you look at fixed points of involutions, which are classical groups. But for general groups, much less is known. So what's known for general groups? And that's what I want to focus on today. So there have been a lot of people who worked on some special cases, but one of the first constructions for general reductive groups was the introduction of the depth by Moy and Prasad in 1996. So what does it mean? So if we think of representations, so Mark Wieder always tells me he thinks of them as fish swimming in the ocean. So let's imagine we have the ocean here, and then we have some fish swimming in there. These are the representations. And what Moy and Prasad did, they said, OK, give me a representation, and I tell you how deep in the ocean it is. So the depth, I want to denote it in this direction. The depth is a non-negative real number, so 0 or a positive real number. And Moy and Prasad, they described all the depths 0 representation. And I should say that Morris did the same slightly earlier in 1993 using a bit different approach. So that means that we now know how to to deal with the representation that swim here on the surface of our ocean, the depth 0 case. Up to actually, so they said they correspond to representations of finite groups. So assuming you understand the representation theory of finite group, then you understand the depth 0 representation. All right, so that was the first step. Now we want to go deeper in the ocean. And in 1998, Jeff Adler, oh, I should use a different color. Let me use red for this. So Jeff Adler gave a construction that brings us down in the ocean. So he constructs some fish that have positive depths. And then 3 years later, 2001, JKU, he looked at Jeff's construction and extended it vastly. So build on this so that we now get much more representations everywhere here. So there are a lot. Now the question is, okay, great, finally we have supercars representation. It was very difficult to write them down. If we don't work with complex representation, this was unknown until very recently. But so there they are. Do we have everything? Or can we do better? So in 2007, Julie Kim, she proved that actually use representations yield all supercuspal representations. But with a small caveat, she assumed that the prime is very large. So the prime P of our p-adic field, the characteristic of the residue field, if this prime is sufficiently large, let's say I want to draw in this direction the prime P, and let's say this is the zone here where P is very large. So what Julie Kim showed is that if P is very large, we get all representations. So we know all the fish that swim there. They all come from use construction. But so the question is, what happens if P is not very large? And a partial answer was given in 2014 by Mark Reeder and JKU. What they did is they constructed so-called Epp Logic representations. And the nice thing about their construction is that it works for all primes P. And the construction works for all P. So what are these Epp Logic representations? So the Epp Logic zone of the ocean is the upper zone of the ocean. It's a zone that can be reached by sunlight. So the Epp Logic representations are those that swim in the upper zone here. That are those that can be reached by sunlight. And so in other words, these are the representation of smallest positive depth. And they gave a construction that produces some of them. And so actually they said, okay, take some nice object, and then we give you a Epp Logic representation. The question was still if these nice objects exist. They showed they exist for P sufficiently large, but it wasn't clear if they exist for small primes. So around 2017, 2016, partially in a joint paper with Beth Romano, we showed that actually the ingredients for Vida use construction they exist for all primes P. If they exist for large primes P. Which means that we actually now managed to enter this zone. So Rita and you gave a construction, but it wasn't clear we have the input that's needed. And we showed actually the input is needed. So that means we can construct more representations here that were not yet constructed by JKU and Jeff Adler earlier. So that means the red dots, the U representation, they are not everything. There is more. So this means, if you look at the picture, two big questions remain. One question is, so these are only Epp Logic representations. Do we have more here? In the end, we want to find all representations. We want to find all Supercars representations so that we can talk about the local Langlands correspondence and talk about all kinds of things. We want to know everything. And I believe there are more here. And the second question is, I've drawn a bunch of red dots here. Julie Kim showed that for P very, very large, we have everything. So the question is, how large does P actually have to be to get everything from U's representation? U's construction is very nice. A lot of people used it for various things. So it would be nice to know that actually U's construction is exhaustive in a much larger region. So I want to find a prime, say maybe here this is the zone where P is large, not very large, just minor condition. And want to say here it's actually exhaustive, here we get everything. So these two question marks, that's my current and future work in progress. And I want to report a bit on it today. I want to tell you first what I expect this question mark to be. Wait. Yes, I'll say a bit more later. Just bear with me for 5-10 minutes, and then all right, so my expected theorem. So let's be optimistic. Let's say I do it this year. What do I want to show? So suppose the group G splits over time extension of K. So that's what people always assume. In this area, people always work with groups that split over time extension, except my thesis. But before that, people always restrict to this case. In particular, JKU starts with G splits over time extension. So if we want to show exhaustion, of course, we have to assume it. And assume that P does not divide the order of the Y group of G. So W is the Y group of G. And that's what I mean with P large. So by P large, I mean P not dividing the order of the Y group. And I've written down for you the orders of the Y group up there. So you see, for AN, you exclude all the primes that are smaller than n+1, but for the exceptional group, you exclude at most 2, 3, 5, and 7. So even though the order of the Y group is pretty large, the primes you actually exclude are not that many. So it's a reasonable amount of primes you exclude. So suppose this happens. Then I expect that U's construction yields all Supercars representations. So that's the statement I am aiming for. Let me make a few remarks about this. So first of all, to answer Yanni's question, so the primes I exclude are written up there, just a bunch. What Julie Kim does is she writes a bunch of conditions and says, OK, assume this, that, and so on. And it's really difficult to figure out what primes she excludes. But just to give you an example, for GLN, Julie Kim assumes that P is at least should be at least n should be large, at least larger than n, and at least larger than E. What is E? Where E is the absolute ramification index of K. So that means if you take a field K whose ramification index over QP is very large, then Julie Kim excludes a lot of primes. So it depends on the field she chooses. While what I exclude is just the first part. I just exclude all the primes that are smaller or equal to n. To be honest, I think what Julie Kim excludes is rather the product of N and E. Loki and Ma, they worked out that it suffices to exclude something like the product plus 1, the maximum of the product plus 1 and 2n plus 1 or something like this. So as I said, it's difficult to look at Julie Kim's conditions and figure out what she actually excludes. So that's just the lower bound, but it shows you already that we exclude all the primes that are smaller or equal to the absolute ramification index. So if you give me a field with a large absolute ramification index, then you exclude way too much.
Is P bigger than n the truth field?
Sorry?
Is P bigger than n the truth field?
The what? Truth?
Truth. I mean, is this the real type?
So I believe that what I write down is basically the optima. I'll give me 5 more minutes and then I answer your question. So that's the topic for today. Whenever you're asked, wait 5 minutes.
For E, is that the exponential map is used?
Yes, so what Julie Kim does, she uses the exponential map from the Lie algebra to the group, and that's precisely where this is coming from. Yeah. All right, so maybe just as a remark, so my attempt to prove is totally different from Julie Kim's approach. So what Julie Kim does, she uses the Plancherel theorem and uses harmonic analysis and uses the exponential map to work on the Lie algebra and then transfer things to the group. Well, I work mainly with the building, use some geometric invariant theoretic ideas, and basically what I try to do is, if you give me a representation, I try to give you the JKU datum. So maybe I should remark that more precisely, for every irreducible representation that you give me, I exhibit a type, a Bushnell-Kutzko type. It's one of the types that Julie Kim wrote down together with JKU. So JKU wrote down all these supercuspidal representations by starting from a datum, getting a representation of a compact open subgroup roughly, and inducing it. And Julie Kim and JKU together observed that actually from this you can get types in a much more general setting. So what do I mean by exhibit a type? What is a type? So if you ask Moy and Prasad, if you give a representation to Moy and Prasad, they tell you, okay, we give you the depth of the representation, we tell you where the fish swims, and we also tell you that if you give us the representation at the depth that we determine, there is some nice subrepresentation. It's a character such that this representation restricted to this subgroup of a certain depth contains this character. So it's something nice about it. The disadvantage is that there are many, many representations that if you restrict them to this depth, to this open compact subgroup of a certain depth, they also contain the same character. So they call it an unrefined K-type because it's unrefined. It doesn't tell you enough about the representation. So there are a lot that have the same. So what do I do now? So if you give me a representation, I give you a compact open subgroup that's much larger than the usually much larger than the subgroup that Moy and Prasad give you. And together with it, I give you some representation of the compact open subgroup. And the representation you gave me, if you restrict it to the compact open subgroup, it contains this representation. And the nice feature about it is that if you give me any other representation that contains, when restricted to this open subgroup, the same representation, then these two lie in the same Bernstein component. So this representation of the open subgroup that I produce for you covers a lot of information about the representation. It determines the Bernstein component that this representation lives in. And for supercuspidal representation, it does even more. If you give me a supercuspidal representation, I give you the U datum and say, here, see, here's the datum, run U construction, and you get back your representation. All right, so that's the idea. So now I want to say a bit about the question that Aris raised. So why should P not divide the order of the Y group. Oops. Is this the best way that we can do? Or maybe tomorrow someone else comes and says, oh, I proved it for all primes P. I mean, of course, G should be tame, split over tame extension, because that's what JKU assumes. But why this one? So the input for JKU's construction, the input is a rather, maybe on the first glance, complicated datum. But one of the key features, one of the important things in his input is something which I'm going to explain afterwards. So it's called a good semi-simple element in the Lie algebra. So I'll tell you what this means. In the Lie algebra of a tame torus. By tame torus, I mean a torus that splits over a tamely ramified extension. So that's one of the input for JKU's construction. And what I've recently shown, so it's on the archive since January, is the following. Let me put a small star here, because I'm slightly lying at you. So the equivalence I'm writing down works in almost all cases. And if you want to know the precise equivalence, have a look at my paper.
Is it really 19?
Oh, now I understand. Thank you. Wait, but I put 18 there. Yes, good. Complicated. I can post it again next year. Okay. So I claim the following are equivalent. First, G splits over a tame extension. And P does not divide the order of the Y group. So this is precisely what I assume in my expected theory. And the second is that all tori in G, or all tori of G, are tame. So all tori split over a tamely ramified extension. I put a little star here because for some non-split forms of the some non-split inner forms of the split group of type AN, DL, and E6, you have to modify it slightly. You have a slightly weaker condition here, but only for some of the inner forms that are non-split inner forms of a split group. And you can look at my paper that already exists. So that means in order to actually get the tame torus that you uses, we need to assume that G splits over tame extension and P doesn't divide the order of the Y group. In other words, when we don't assume this, they are non-tame tori, and I believe you can get something out of them as well. And I should say that in addition, if 1 and 2 hold, then I also show that for every torus T inside our group, for every maximal torus T inside G, every multi-set filtration coset so I'll define this afterwards as well. So every multi-set filtration coset of the Lie algebra of the torus, so let me call this just frag T, contains actually a good semi-simple element. So that means up to this star, this small exception, really this condition is precisely what we need in order to get the input for U's construction. All right. So let me tell you the things that I omitted. So what are all these objects? So first of all, if you can't read, let me know. Is it okay?
Not really.
Okay. Let's Are there any questions? Maybe questions that I can answer in 5 minutes? All right, so the statement, maybe I put it up, was that these two are equivalent, and if they hold, we get our nice, good, semi-simple elements. So what are all these objects involved? So what is the Moy-Prasad filtration of the torus T? So Moy-Prasad filtration. So if you take R to be some real number, T being the Lie algebra of the torus, then T sub R, these are all the elements X inside the Lie algebra of the torus, such that the valuation of d of phi of X is greater or equal to R for every character phi of the torus. And d of phi is the Lie algebra version of it over k bar. So you take all the characters of the torus, look at the valuation, and it should be greater or equal to R. That's the R's filtration subgroup. So for example, if the Lie algebra is one-dimensional, so if it's just the field K, then T sub n for n being some integer is just pi to the n O living inside K. So you define a filtration of K via pi to the n O.
Is the torus split?
No, not necessarily.
So how do you normalize the valuation? Uniformizing is 1 and it remains 1.
Yes. So I like different people do it differently. Good question. I normalize it such that the valuation of my uniformizer in K is 1, and if I have an extension of K, it just extended the valuation. But you have to be careful. Some people normalize it for each field extension. It doesn't matter in the end. It just shifts. It scales everything if you change the valuation. Yeah. And then to be a Moy-Prasad filtration coset. Moy-Prasad filtration coset is just something of the from X plus T sub R plus, where X lives in the R's filtration subgroup. And what is T sub R plus? This just means it's T sub R plus a very small epsilon. In other words, it's a union of T sub S for S greater than R. So if you have a jump, it's the next filtration subgroup. And we look at all these cosets. And the claim is that all these cosets contain particularly nice elements. So what are these particularly nice elements? X inside T sub R is called good semi-simple. I mean semi-simple because it's inside T anyways. Good semi-simple of depth R if the following holds. If the valuation of d alpha of X is precisely R, so not just greater or equal, but precisely R, or if d alpha of X is equal to 0 for all roots alpha of our group. So that means we want for every root to have equality here, or we want it just to vanish. So it's somehow, it's very regular, it's very nice in some sense. So for example, if G is equal to GL3 over the field K being Q17, and then if we look at, so we can look inside here at the diagonal matrices, so that's T, and if we look at the torus, if we look at the element that has 1, 2, 3 on the diagonal, then what are the roots? The roots are just the differences between diagonal elements, so it's 1, 1, 2, and plus and minus 1, plus and minus 2. So that means if you look at the valuation of all the roots applied to this, you get 0 in all cases, so this element is good of depth 0. But on the other hand, if you look at the element 1, 2, 19, the difference here, so the root applied, the root corresponding to this pair is 1. The difference here is 17, so the valuation of 17 is 1, the valuation of 1 is 0. So you have different valuations, so you can't find an R such that you always get the same. So this means this element is not good. It's not good for any depth. And I claim that whatever group you start with, as long as it splits over a time extension, P doesn't divide the order of the Y group, and every multi-set filtration coset that you like to consider, you can always find such a nice element, such a good semi-simple element. It's an easy exercise for GLN and the eigenitors, but it gets more complicated and more complicated situations. All right, so maybe I don't want to say much about the proof. You can find it on the archive. Just a few words. The proof is based on some Galois cohomological consideration, and I mean it uses a lot about the structure theory of the Y group, structure theory of local fields, structure theory of p-adic groups over local fields. And it's not too long, just 20 pages. So okay, so that's what I wanted to say about the expected theorem that I just erased and why I believe it's optimal. Now I want to show you a bit how to actually get the supercusp representations so that you get a feeling for how the construction works. And what I do for exhaustion is basically just go in the other direction, give you the data that I talk about. So construction of supercusp representations. So there's a folklore conjecture that all supercusp representations arise in this way that I'm going to write down. The way is as follows. So first, you construct a representation of a compact open subgroup. Let me call the representation rho of a compact open subgroup. So for example, of GLN ZP inside GLN of QP. Let's call it K. And the second step is then that you construct a representation of the group G of K from the representation of the compact open subgroup from rho. And this is just compact induction. So the difficulty in doing this really lies in this first part, to find a nice compact open subgroup and a nice representation of it, so that if you induce it in step 2, you get a supercusp representation. And it's known that if what you induce is irreducible, then it's supercuspital. So all you need to find, as if it's so easy, is a nice representation of a compact open subgroup. So I want to give you an example for this, and then hand wave a bit to tell you what JKU does. So I want to work you through the construction of reader and U, which, remember, that's the Epp Logic zone here. These are the white dots up here. And this is actually, if P is sufficiently large, it's a special case of what Jeff Adler did, which was then generalized by JKU. All right, so what's the construction? There are two pieces of input for it. The first is you take, as over there, an open compact subgroup. So inside the K points of our group, we take something called GX0, GXR1, and GXR2. These are three numbers on my good thing today. These are three open compact subgroups. And this is called the beginning of the multi-site filtration. So let me give you a quick idea of what this is if you haven't seen it before. So the X here, this is a point in the building, in the p-adic building. All it does is it encodes a choice of a maximal split torus and a parametrization of root groups. And what this R does, this is just the depth. That's the depth of the ocean. So that's a non-negative real number, and that encodes a torus for you and a root group parameterization. So, for example, how do we get a multi-site filtration out of this? So we have a torus, so we can define a filtration for the torus. I've already defined a filtration for the torus for you. I think it got erased. Oh no, it's up there. I defined a filtration of the Lie algebra of the torus. You can do the same thing basically for the torus. So for example, here I have the example of GL2 or SL2, whichever you like, so you intersect with the invertible elements or those of determinant 1. So the red part, the diagonal, is the torus that I've chosen. And you see that this filtration translates into filtration here by ZP 1 plus PZ 1 plus PZP squared, and so on. And then the other part is the root groups. So you have the filtration of the torus, and then you pair it with the root group filtration. And this X tells you how to do this. So there are two, in this setting, there are up to conjugation and up to some small shifts. There are two possibilities. You either start with ZP, then you have inside there PZP, P squared ZP. That's one possibility. Or the other is that you start already slightly filter based. I mean, it's a slightly smaller subgroup and one of the root groups, and then you first only change the torus, then you change the root groups, then the torus, then the root groups. And that's basically how it works. You always define a filtration for the torus, like this one over there, and then you define a filtration for the root groups, and you just have to put them together. And this small index X, that tells you how to do it. So in this example, this is the zeros filtration subgroup, GX0. This is the first filtration subgroup. Let me keep them. This is the first filtration subgroup, so GX-R1. R1 just means the first one. This is the next. This is GX-R2, and so on. So 0 is the first, R1 is the second, R2 is the third. And what we then do is they study the Epp Logic Representation, which means they only go to this first step, basically. That means Epp Logic. Depth 0 means, roughly speaking, induced from this zero filtration subgroup. Epp Logic means induced from this next step, from this R1 step. So that's why they look at these filtration subgroups. Yes?
For X, do you really need a point of the building or just a simplex of the building?
So for this GX0, a simplex suffices. So the building is a simplicial complex. If depending on what point you choose, what changes is the next filtration step. So the filtration actually depend on the actual point in the building. You can even describe the building using these filtrations in some way.
And also, the building does not really see the center of the group.
No, so that's why there are different ways to approach it. So for the U construction, if you really want to induce a supercars representation, you take the image and the building of the what do you call it? The derived group of the group. So you ignore the center. But if you want to work with types, if you want to get compact open subgroups, you take the whole building. Of course, it doesn't matter where you are. If you shift by the center, nothing changes. But it's important if you describe this. The first group, what it's roughly speaking is it's the stabilizer of the point in the building up to some finite index. And for this, you need to use the enlarged building. So there are different types of buildings which are the same for semi-simple groups. And if you have a general reductive group, then you have a center, and you can extend this building basically by the center. That was what the question was about. Further questions? Okay, so that was the first part of the input. Now the second part of the input. So we have already a compact open subgroup now. We need where to induce from. Now we have to get a representation of it. So what do? They say, okay, as a second input, we want a map from GXR1 mod GXR2. These two subgroups. It's a finite group. It's actually an FP. It turns out to be an FQ vector space to FQ. Let's call this chi. So this should be some character, and they want it to be nice. So they say that should be a stable function or a stable vector. I say later the precise definition. The way to think of it is that it's somehow very regular. So for example, let me actually put this up. So the example to keep in mind, if G is SA2, what do we get? So let's take the right filtration. For the right filtration over there, we get GXR1 mod GXR2. So if you look at this, between these two groups, the thing that changes are the off-diagonal elements. So if you look at the quotient, this quotient is actually isomorphic to just FP bar FQ. Sorry, it's isomorphic to FQ on the antidiagonal elements with respect to addition. So this quotient is just isomorphic to this. And we want to have a character of it, so we want to send it to FQ. And the way we can send it to it is, for example, we take xy, the element xy, and we send it to x plus y. Other things we could do is just send xy to any linear combination, like a times x plus b times y, as long as a and b, the coefficients, are non-zero. So what we are not allowed to do is to send it to x or y. So that means it's somehow regular. And this actually corresponds in some sense to the good semi-simple elements. So I've talked about good semi-simple elements that were used by JKU, and what Vida and Yu did is they singled out a stronger condition that actually works for all primes p. So let me maybe say as a remark for those who are interested in this, how does this correspond to a good semi-simple element? So it turns out that GXR1 mod GXR2, this is actually isomorphic to a Lie algebra filtration that's constructed in the same way. And sorry, this is an abelian group, yes. Yeah. And these two are isomorphic, so we can map to it from GXR1. And the whole thing should map to FQ. This is the character chi we choose. And if P is large, then it turns out that we can instead take a character from this whole subgroup of the Lie algebra to the ring of integer and quotient out by the maximal ideal to go to FQ. And this map here, this corresponds to the good semi-simple element. So we can choose a good semi-simple element such that if you take a pairing with this Lie algebra, you end up in O, and if you compose, you get precisely this character. So what they singled out as a stable vector is actually coming for large P from these good semi-simple elements. Okay, so let's assume we have these things now, for example, this vector. What do we do then? So we want to build now a representation of a compact open subgroup. So we have compact open subgroup GXR1, the Epp Logic one, which maps to GXR1 mod GXR2. Then we have our character chi, which goes to FQ. And we can compose this with an additive character to the complex numbers. And if we do this, we get a character let's call it phi sub chi, of our compact open subgroup. So that's a representation of a compact open subgroup, so we can compactly induce this representation from GXR1 to the whole group of phi of chi. So in other words, this is as usual. These are just the functions from the k points of the group to C, such that f of kg is equal to phi sub chi of k. F of g is usual for induction, but now since it's compact induction, f should be locally constant and compactly supported. And g acts on it via right translation. And this is almost the representation we want. It turns out this representation is the finite direct sum of some representations pi i's. Let's call them pi I. And these pi I, these are the Epp Logic representations. You can get any single of these pi i's by simply extending phi to a slightly larger compact open subgroup and inducing them. So all of them are induced from a compact open subgroup. So that's the way we then build the representations. Induce from this first filtration subgroup a nice representational character. What Jeff Adler and JKU do, or more JKU in general, is he takes not only one group, but he takes Levy subgroups of his groups, takes characters of all these Levy subgroups, or actually twisted Levy subgroups, so Levy's after an extension. He takes all these characters together, and he takes a depth 0 representation, so this depth 0 part, which was a representation of a finite group, and puts everything together, builds a compact open subgroup out of this, which is larger than just this filtration subgroup by Moore and Prasad. It's built out of a lot of filtration subgroups for the Levy subgroups, and then he induces this up. So it's basically the idea of taking depth 0, taking this idea, which was much later, and putting everything together, building a much more complicated compact open subgroup, which is a much more complicated representation, which is no longer a character in general, and inducing everything up. So that's how it works. Okay, in the remaining minutes, I want to tell you a bit more about the input, about the Moore-Prasad filtration, which crucially underlies everything. So, all this black versus ink. Okay. Let me use another blackboard. So why is this Moore-Prasad filtration so nice? So more about the Moore-Prasad filtration. So first of all, it's a filtration by compact open subgroups. You can understand the whole group by studying the groups that all the quotients, which are all some finite objects. But the nice thing about it is that there's a lot of structure to it. So if you look at GX0 or GXR1, so what is it? So in this case, if you look at these two groups, if you look at what you get is GL2 over the finite field. And if you look at the quotient here, what you get is just the diagonal matrices over the finite field. In both cases, you get a group, and that's what always happens. This GX0 or GXR1, this can be identified with the K point, the FQ points of a reductive group. It's often called the reductive quotient because what it actually is, it turns out to be the reductive quotient of the special fiber of a parahoic group scheme that Weird and Tietz attached to a point of the building. So this quotient is particularly nice. It's a group.
Filtration is by invariant subgroup always.
Sorry, can you
The
repeat?
filtration is by invariant subgroups.
What do you mean the
The Moy-Prasad filtration.
The Moy-Prasad filtration is the one that I outlined.
It's all invariant subgroups, so you can take the curve.
Oh, it's by normal subgroups, yes. Oh, sorry. French, yeah. Took me some time, sorry. Yes, so very, very important feature is that this filtration is a filtration by normal subgroups. So you can take all these quotients, and you can do even more. So, but let me maybe say something more about the first one, and then I can tell you more things you can do. So this is a reductive group. This is what the depth 0 representation comes from. It's a representation of this reductive group. And I wanted to say that Briel and Tietz in the 80s, they described this group explicitly in combinatorial terms. They gave a root datum for it. So this group is rather well understood. Then you can look at all the other quotients, GX-R1, mod GX-R2, and all the others. If you do this over here, what you get here is just the 2x2 matrices over the finite field. If you do it here, we did it earlier. For this, you just get the antidiagonal matrices under addition, so that multiplication translates into addition. And so this is always an FQ vector space. And since Pierre Delaine pointed out that actually these are normal subgroups, we have GX-R1 sitting inside GX-R0 as a normal subgroup, so we can act on it via conjugation and preserve this subgroup. And this action descends to an action of the quotients. Oops. And now we have an algebraic group acting on a vector space, and magically this turns out to be a linear algebraic action. So this is particularly nice. And this is at the heart of the definition of stable vectors. So I said we take, okay, I erased the reader and you take a stable vector inside the dual of this. Stable vector here just means stable in the sense of invariant theory, which means you base change to the algebraic closure, and then you require the orbit inside here to be Zariski closed and the stabilizer to be finite. So that's the definition that Mumford gave in geometric invariant theory. But the way to think of it is just it's somehow a very regular element. Actually, for large primes P, it turns out that these stable vectors, they precisely correspond to regular semi-simple elements if you view this inside some. So you can embed this quotient into a Lie algebra, and then it turns out that stable vectors are the same as regular semi-simple elements. So it's just think of something nice, regular semi-simple. All right. So in order to get the representations, we have to understand these spaces because we want to find stable vectors in here, and we want to understand this filtration. So the question is, what are these spaces? Thanks to Briel and Tietz, we know what the group is, and what I did, put it on the archive in 2000. It's in my thesis from 2016 at least. Is I gave a description of these representations, GX0 mod GX-R1 acting on GX-R1 mod GX-R2 in various ways. So for example, I described it in terms of Weyl modules and the adjoint representation. So that's a way to describe it very explicitly. I also described it in a generalized Wienberg-Levy setting. And I should mention that this was done by Vida and U for large primes before. But it works also for small primes. This just means I described it as a graded piece in a Lie algebra, basically. If you did, I just put it basically on the blackboard in case you've heard about it and like to talk to me about it. And actually, the underlying thing, the key innovation that made all of this possible is that I constructed a global model for the multi-site filtration quotients. Quotient representations. So I provided, basically what I did is I provided a group, some group over the integer or some primes inverted acting on some free Z module such that if you base change to the prime you're interested in, you get the multi-site filtration that you're looking for. So this is just this.
Well, what you don't need be bigger than the Coxeter number?
No, so that's what Vida and U do. They need it more precisely. So Wien-Berg-Levy setting means you have a group with an order M automorphism acting on it, and the Lie algebra decomposes in M spaces, and you pick out one of the spaces. And for this, you want P not to divide the order M of the automorphism, because otherwise it doesn't. All the things don't work. You don't have roots of M's root of unity inside Fp if P divides M. What I do is I still work in the setting. I allow P to divide the order of the automorphism. So I talk then about not an order M automorphism anymore, but the mth root of unity acting on it, and we can still talk about the fixed points of this action, and we still get the decomposition of the Lie algebra, even though we don't have the roots of unities anymore. Further questions? All right, so then let me just finish by saying, so that means we have a rather good understanding now of the multi-site filtration, and this helped us to show that. So now what do we actually want to show? So Vida and U, they said we want to have stable vectors in the multi-site filtration, and then we get our Epp Logic representations out of it. So Vida and U, they gave a criterion for the existence of stable vectors over FQ bar. Stable vectors, again, geometric invariant setting, which worked for large primes P, which worked if P doesn't divide the order of M, where M it's related to the point P, so to the point X. So for example, for SLN, they didn't allow primes to divide N. And what I did, partially in a joint paper with Beth Romano, is to show that the criterion holds for all primes P. Oops. The problem is the proof of Vida and U really heavily relies on the prime number P to be large, because they use Wien-Berg-Levy theory. But the criterion they give is solely, it's combinatorial. They wrote down a list of groups and said, okay, for this group and for this point of the building, we have stable vectors here and there. So it's something you can actually check. It doesn't see the prime number P, but the proof just can't be, the proof itself doesn't work for small primes P. So what we did is we used this global model to say, oh, basically the multi-site filtrations all look the same. They are all special fibers. And then we say, oh, for large primes P, we know what it is. Now we transfer the result to small primes, and we know that it exists for small primes if and only if it exists for large primes, where we know the existence. Okay, thank you very much.